Okay, ready for the next presentation? Here we go. Let me hand over to Jan Pistulka from STMicroelectronics, EMEA system engineer. He will talk about virtualization in the world of automotive MCUs. Jan, the stage is yours.
Hello, and welcome everybody to this presentation about virtualization in the world of automotive MCUs. I'm Jan Pistulka, working at STMicroelectronics for more than 6 years, currently at position of EMEA system engineer in Munich. In the upcoming roughly 30 minutes, I will show you a brief history of virtualization, map this to automotive and its requirements, show you what does it bring to automotive industry, and tell you how is the hardware dealing with that. Let's start with a little bit of history overview. You can see the timeline over here. I just picked some interesting dates. The virtualization itself first showed up with the mainframe computers in 1960s. They were one big room, costly, and unfortunately, or fortunately for the virtualization, underutilized. Then the guys, Popek and Goldberg, summarized the general requirements for virtualization, like equivalence, meaning virtual machines are on the same level, resource control, and efficiency. 20 years after that, the first cloud computing was referenced in an internal document of Compaq. That was in 1996. Amazon came with their web services 10 years later, and already 2 years after this, the virtualization for mobiles was introduced. It took 3 more years for ARM to introduce the virtualization extension to the ARM v7 architecture with the Cortex-A7. So that application processor provides a set of hardware features for virtualization, interrupts, exception levels, and all what we will talk about. And today we are in 2020 having microcontrollers that includes virtualization as well. But what is the virtualization? In general, it is an approach which combines software and hardware measures in order to utilize the resources. Very similar to the story with the mainframe computers. The guy responsible for the virtualization in the system is the so-called hypervisor, or in another name, VMM, which stands for Virtual Machine Manager. There are two types of this manager, very simply named, Type 1 and Type 2, and they are different in many aspects based on the underlying hardware, whether it has a support for virtualization, the so-called Type 1, having direct interaction with the hardware and thus reducing the software overhead. Or the hardware does not have the support, and an additional layer, the host operating system, is in between to do this separation. That's the type 2. We will come back to the comparison of these two types later, but now I would like to link the virtualization as here introduced to the automotive. At the very beginning of networking in cars, the ECUs, if they were even connected, those connections were one-to-one by some low-speed protocol, and they did not create any big network at the time, as simply there was no need for that. But as the functions were coming, adding more ECUs, also the need for information exchange and interaction increased. In the next generation, there were already several separated networks. The units were grouped to body, powertrain, etc., with few components interacting with other, let's call them branches. The third generation brought consolidation with the central gateway, where the units are connected via backbone to the central piece and are handling complex functions already. Further consolidation of these 30 to 100 plus ECUs started by the central gateway architecture continues with the domain controllers, where we are about today, towards the domain. The complexity is again increasing, but the consolidation is taking some of it off. The outlook is going on towards complete centralization on the right-hand side, with a zone where all the functionality which are in the particular corner of the car will be integrated. Having said that, the missing link now is the connection to the virtualization itself. So let's focus on the today's trend, the domain architecture. The functions which were extra or optional a couple of years back are nowadays pretty much standard. On top of the customer wishes, the legislation with its demands to safety functions is increasing once every few years, and the ECUs are emerging in the cars to cover these needs. Not only the number of ECUs, but also the duties have changed, and it's not about quantity, but complexity as the different, we can call them services are coming, and to have sophisticated software without sophisticated hardware would be like having a muscle car without a fuel or electric vehicle with drained battery pack. The units are there not alone, but part of the network communicating with each other, and that means all the cables must be designed, routed, and connected to sometimes difficult places. All of these are the contributors to the big network inside of today's car, tends to really 100 plus ECUs depending on the model and customer configuration. The job of the domain architecture is to combine the functionalities together by integrating them into one performant hardware and bringing on top of some other benefits that just rationalizing the network. It is, for example, reducing the number of ECUs and consolidating the functionalities. We will take these 4 ECUs that you can see in the upper right corner, or we can call them also applications side, and we will integrate them into the domain. As before, there were these 4 independent ECUs. Now they will become one domain. And each, let's say, main application will be a virtual machine where the resources are managed by the hypervisor. Because the applications are completely independent of each other, can have mixed criticality of AC levels, the domain controller must get along with it. Thanks to the integration, the different functionalities are coming together. There must be assured that they will not influence each other. That means freedom from interference and clear separation by software or hardware measures. It must be guaranteed that they are separated, and important is that they are deterministic. Nobody would be happy with a solution which works 80% of the time and because of non-determinism misses the other 20% of cases. This can be achieved by the quality of services inside the chip so that everybody will get the bandwidth needed and the starvation is avoided. Because whatever communication among those, in example 4, was happening via CAN, Ethernet, or in outside, will now be done via sockets, buffers, or other internal mechanisms. The separation helps with the integration and also verification and validation, as in one ECU there can be around really 100 software components from 100 different vendors. Having said that, such amount of software needs hardware measures, cooperation and help in order to get the best performance out of the ECU. Now, let's quickly compare with and without virtualization. Virtualization means sharing of resources, whether those are execution cores, DMAs, peripherals, or memory, and at the same time maintaining the independence from each other. This is a strong requirement that if I have one or two or four virtual machines, they don't know the difference. They must not know the difference. Without virtualization, the assignment is one-to-one. One application running on one core, one peripheral used by one application, and that means always to have redundancy of these resources, cores including. With virtualization, it's not anymore the case, as it brings the utilization and sharing with it. The virtual machines can be mapped to cores in several different scenarios. One virtual machine running on one core, multiple virtual machines on one core, and one virtual machine on several cores. Then, of course, mixture of these three scenarios. Similar story is it with peripherals as well. They can be virtualized and shared, but about that we will talk in a couple slides. At the beginning, we were talking about the type 1 versus type 2 characteristics, and I promise you the comparison of them. As you may expect, it will be kind of a trade-off between software versus hardware costs, overhead, and separation. As mentioned several times during the last EMCC, the free lunch is over, and this metaphor is fitting to this perfectly well. Let's swap the order now and start with what is called the hosted software solution, the Type 2. As there are no specific features of the hardware accelerating the virtualization, we can say it is more independent of the hardware and thus easier to port. But on the other side or other hand, what could have been done in hardware is now done only by software, and in the end effect, eating our cake of performance. This also implies that this software or host operating system must be verified with the application as he's doing the separation, in this case, software separation. Here is an example of a solution without hardware support. And as you can see, the approach here is a master-slave. The master manages the accesses to the shared hardware resources, configure it, take care of the faults, and the hypervisor layer, if I simplify it, it's just doing the interface for the slaves. But it's like a more or less server-client solution. The Type 1, on the other hand, is almost like the opposite. Because it has hardware features for virtualization, it's reducing the software overhead, which makes it run faster. But we need to take the assumption that the difference between left and right is just relative support for virtualization, but other than that, the system are the same with same frequency. But as a downside on the type 1, it makes him more dependent on the hardware, which is the cost for a physical separation. At the end, the costs are either on the hardware or the software side. And this is how we have decided to implement the Type 1. That means the hardware way. For sure, the enabler is the ARM Cortex R52, optimized for hard real-time and safety-critical application with its native support for virtualization. That includes, of course, virtual interrupts, 3 privilege levels, ARM called them exception levels, and also 2 levels of memory protection unit. The advantage of R52 is that it's able or capable of propagating natively to the buses the VMID, which stands for Virtual Machine Identification Number, and that identifies the currently running virtual machine on the core to the buses along with the instructions. So based on the specific VM ID, only wanted VMs, meaning virtual machines, can access the memory region or have the writes on a peripheral, and the unwanted, they will be blocked. But it is not just this core which everybody can license and virtualization is done. It's about the overall system, as one player does not make a team. The system consists of not only the R52s as initiators, but other masters as well, like DMAs, another cores in case of mixed system, like the Cortex M4s, or peripherals which behave like masters, and they natively does not have the VMID. About all these has to be taken care of within the implementation and design of the microcontroller. When all the masters can identify themselves, or under the assumption that they can identify themselves, the destinations, targets, slaves, they must have a measure or capability to verify such transactions and gate it according to the settings, like peripheral protection or firewall. We call it firewall because the NOC stands for network on chip. Integrating the applications into one chip brings the traffic from outside to the inside, and that means we have to make sure that in the system exists a mechanism that guarantees a bandwidth and avoid starvation. Coming to sharing of peripherals, there are different strategies how to manage peripherals and multiple virtual machines. It depends on several factors: the design of the peripheral itself, and then for sure on the integration inside the system. Because, for example, just with a memory map, you can achieve a lot of things, to be honest. The best case is on the complete left-hand side. If it is when there is enough hardware, resources, peripherals, whatever you want to call them, to cover all the virtual machines. This will guarantee the maximum freedom from interference, because if two initiators will access two targets via network on chip, it will happen completely combinatorial. That means in parallel. At the same time, this does not necessarily mean that you will need 4 Ethernet for 4 virtual machines, but that you can assign, for example, 4 queues or any other hardware granularity which will provide the needed function. The hypervisor is there to configure the virtual machines and resources to supervise them and collect errors. So this option is giving the best performance, but at the cost of the hardware, the footprint, which leads to the more cost. Then we come again to the master-slave scenario, but in this case with type 1 hypervisor. And that means he's not only an API and the driver is in the virtual machine itself. This saves the die size, but suffers from less freedom from interference and a little bit of performance. As third option, there is the software virtualization, where the hypervisor is the master and the virtual machines are requesting through the hypervisor calls the actions on the peripherals. Having said that, makes maybe a bit of a confusion, but if I add the information that the hypervisor is in every single R52 core, it makes him local from the core point of view and not a master which is only one instance in overall system and is accessed from everywhere. Because we are talking about microcontrollers and not microprocessors, the memory management unit based solution is shaded out. But the MMU is doing the mapping and remapping of logical to physical addresses, but really for microcontrollers, not relevant. As you can imagine, in one microcontroller, there will be a mixture of these strategies because it's matter of performance, efficiency, die size, or footprint and money. Yeah. We are slowly coming to an end, and it's time to talk about what is done and when it's done. After power on reset, the core goes to the highest privilege level. It can be achieved either per design or per software transition. For R52, it is the exception level 2 called hypervisor. The hypervisor is kind of ultimate master inside a system. He's the one configuring the barriers like firewalls and memory protection unit for lower levels, but also assigning the peripherals to the virtual machines by the VMIDs. When this system configuration is done, the VMID in the particular execution core is assigned. The initialization of the core registers is done and the exception level is lowered, as the operating system for VM1 will be on lower level. As already mentioned, the R52 has in total 3 exception levels. The EL2 was already explained. The EL1 is called supervisor and is meant for the operating system of the virtual machine. And the last one, or the third one, is the EL0. This one is for the tasks. So the exception level is lowered and the VM virtual machine 1 is running. When another virtual machine needs to be executed, either triggered by time, so time division multiplexing, or triggered by some event, for example, request for an operation from the other VM, a swap is performed. During this switch or context switch, all relevant information are stored and information valid for the other virtual machine are loaded. This includes CPU registers, global interrupt controller, virtual registers for the virtual interrupts. Could be also firewall settings and MPU settings. This context switch is already and always in jurisdiction of the hypervisor, as he's performing all the actions needed before and after a virtual machine run. Hypervisor is the one with highest privilege in the system, so he is also having an overview of the overall system and the resources. From this moment on, the actions are pretty much the same, changing VMID and preparing everything for the next virtual machine. Here in this example, there are only 2 virtual machines, but the steps don't change with adding any additional second, third, fourth, and so forth. Up till now, it was, let's say, quite general, even though I already showed you a diagram with all the key aspects. So as the last slide, let's show you a real implementation with all these features. This is a block diagram of Stellar. Stellar contains up to 6 Cortex R52s, maximum 5 in lockstep, in 3 clusters, with local RAMs and local PCM, which is new technology in automotive of non-volatile memory. Helps with over-the-air update. As these memories are local in the cluster, they don't need to be protected by the firewall from within the cluster, but only from the outside accesses. As inside the cluster, the only initiators or masters are the R52s with memory protection units. The transaction on the buses are extended by the VMID and master ID. The peripherals are assignable to particular virtual machine by similar mechanism as the memory protection unit in the Cortexes. And for sure, the system is protected by the firewalls as well, checking if the access address or addresses are within the range for specific virtual machine. Having said that, the system RAMs can be for sure partitioned by the firewalls in order to serve not only one virtual machine. For crypto operation, there is the hardware security module, HSM, with Evita full standard. It is only one instance in the system, and in order to have the parallel accesses, the freedom from interference, for the security mechanism, there are multiple AES slides which are capable or which allow you the parallel requests. Finally, other cores like Cortex M4s are there to offload some functionality of the main processing units, for example, for CAN routing. And again, VMID is there as an extension to identify them for the others on the bus. All is connected via the network on chip, providing, as already mentioned, the quality of service to guarantee the bandwidth that, for example, the Ethernet or PCI Express, so that they will not be blocked by others. This brought us to the end of this short tour through the virtualization in the world of automotive MCUs. As you could have seen, the trends are defining the hardware, and for software to run the best way possible, accelerations inside microcontrollers are needed, and support for virtualization is one of them. With this, I would like to thank you for being here with me